Okay, we're off and running with solutions 2. In the last video, we talked a little bit about the parts of a solution. In this video, we're going to qualitatively talk about different types of solutions. And also, we're going to look at the concept of solubility. So what is solubility? Solubility is the amount of a particular substance that will dissolve in a given amount of solvent at a specified temperature and pressure. It's how much can you dissolve. Qualitatively, there are 3 types of solutions centered around this idea of solubility, and the first one is a saturated solution. A saturated solution is the maximum amount of solute that you can dissolve in a given solvent at a constant temperature and pressure. When I talk about saturated solutions, I like to talk about good southern sweet tea or iced tea in the South, where they put so much sugar in it that you could not possibly dissolve anymore, and sometimes when you take a sip of that tea, you can actually taste the granules of sugar that are undissolved in that iced tea. If you don't have a saturated solution, or if you have less solute, I should say, than a saturated solution, you have an unsaturated solution. So saturation is a given point, unsaturated is anything less than that. The final type of solution we'll talk about is a supersaturated solution. That's when you have more stuff dissolved in your solution than you should be able to. And a solution actually has to be tricked into being supersaturated, and it's a very unstable situation. And we'll come back to that a little bit later in the video. Focusing for a second on a saturated solution, it is kind of important to point out that in a saturated solution, even though the maximum amount of solute is dissolved, you're actually going to be in a state of what's called dynamic equilibrium, where the amount of solute dissolved is going to be constant, but which particular ions are dissolved will not be. So if you look at this beaker at the macroscopic level, we have the water and the salt in the bottom of the beaker. At the particle level, what's going on is some of those ions in solution are recrystallizing back into that solid structure, and some of the crystalline solid is dissolving into the solution, but it happens at a constant rate. You can use this idea that no more can be dissolved in order to test what kind of a solution you have. So when we look at the solubility scale and increasing concentration, you have first your unsaturated solution. With your unsaturated solution, if we add more crystals into that solution, those crystals will dissolve in, and the solution will still be homogeneous. It will have one phase. With a saturated solution, however, if we add more crystals to a saturated solution, those crystals are going to fall to the bottom. And they're not going to dissolve, and you're going to have a heterogeneous solution where you're going to have solid at the bottom and then your solution above that. And so we can remember that in that saturated solution, those crystals in the bottom will be in a state of dynamic equilibrium. Well, some of them will dissolve, and at the same time, that solute in solution is going to recrystallize around those crystals. The last one is the supersaturated solution. Again, this is a situation where you have more solute dissolved than you should have. It's an unstable situation. If you add more salt crystals to that solution, the solution is going to immediately start to crystallize out with large crystals that are going to grow in that solution as it tries to get back to the more stable saturated form. One of the ways that we can measure saturation is by looking at what's called a solubility curve. A solubility curve measures the amount of solute that can dissolve at different temperatures. And so if you look along our x-axis here, we're looking at the different temperatures of these solutions. And if you look at the y-axis, we're looking at how much solute you can expect to dissolve. So a couple of different things. One of the things to point out is that temperature has a fairly significant impact on most substances, and that there is a wide variety of solubility curve lines for different substances and how they behave when you dissolve them in water. So let's look at a couple of questions that you might ask relative to a solubility curve. So here's a question. We said, what is the solubility of potassium nitrate in 100 grams of water at 70 degrees Celsius? So take a second, think about that, pause the video and see if you can't jot down an answer. So if we look at the two features here, we have 100 grams of water, so that puts us directly on the curve without having to convert anything. And we're trying to figure saturation out at 70 degrees Celsius. So you're going to go on the x-axis, you're going to find 70 degrees Celsius, and you're going to go up till you meet the line that's labeled potassium nitrate. So potassium is K and nitrate is NO3 1-. So you're looking for that KNO3 curve. And when you do that, you see that little yellow star that we dropped down there on the video, and then, or on the graph, sorry. And then if you read that over, that's going to be about 129 grams of potassium nitrate per 100 grams of water. That would be considered its solubility. Anything less than that 129 grams in that 100 grams of water would be an unsaturated solution. Anything on the curve would be considered a saturated solution. Here's another question. 25 grams of potassium chloride is added to 100 grams of water at 30 degrees Celsius. How much more solute must be added to saturate the solution? Again, take a second, see if you can come up with an answer. Go ahead and pause the video. So we're going to find our potassium chloride curve. So that's KCl. We're going to find 30 degrees Celsius. We're going to drop a star right there on the graph again to find that saturation line. And that saturation line is around, give or take, about 30 grams per 100 grams of water. So if we're at 25 grams, if we want to get to that 36, that means we're going to have to add about 11 more grams of potassium chloride to hit a saturation point. Okay, let's look at one more. Describe a solution made by dissolving 110 grams of sodium nitrate in 20 grams or 200 grams of water at 30 degrees Celsius. So we're going to find sodium nitrate. That's NaNO3. We're going to find that 30-degree temperature mark, and we're going to read up and see what the saturation is, and then we're going to look at that 110 grams. And so the answer to this question is asking you to identify whether this is saturated, unsaturated, or supersaturated. So take a second, pause the video, and jot an answer down. So 110 grams in 200 grams of water would be an unsaturated solution. So you have to be careful here and notice that we're dealing with 200 grams of water and not 100 grams. If this had been in 100 grams of water, then it would have been a saturated solution because it would have been above the curve. But to get to saturation in 200 grams, it would take 220 grams of sodium nitrate. You're well below that, so that is an unsaturated solution. All right, so let's look at factors affecting solubility. In the previous videos, we look at factors affecting the rate of solution formation. That's how fast something will dissolve. These are factors affecting how much will dissolve. And there are two primary considerations, temperature and pressure. So with temperature, it depends on what we're dissolving. So the solubility of most solids in liquids increases with an increasing temperature. And we saw this on the last curve. Most of those lines went up and to the right, although there were some exceptions. And you can go back and look at that solubility curve, and you can see that some of those substances do in fact decrease. And then when we're talking about dissolving gases in liquids, the solubility of most gases in liquids actually decreases with increasing temperature. So warm water can hold less gas than cold water. This is why your warm pop goes flat, carbon dioxide dissolved in a liquid, faster than your cold soda does. When we're talking about how pressure affects solubility, we're specifically dealing with gases and liquids. Solids and liquids are both incompressible states, and so pressure has very little effect on their solubility. But as far as how much gas can dissolve in a liquid, um, pressure generally is directly proportional. So the higher the pressure of a gas above a liquid, the more of that gas will be dissolved in a liquid. And this is referred to as Henry's law. So we have this relationship S1 over P1, or the solubility at some particular pressure, is going to be a constant. So if you increase the pressure, you're going to increase the solubility. So here's a nice graphic on what that looks like. So on the left side, we have gas. So those black dots are supposed to be gas particles in the air above a liquid. And because that plunger is pulled up, there's more volume in the space above the liquid, which means there is less pressure as those gas particles move around. If you increase the pressure by pushing that plunger down, you actually, that increased pressure forces more of that gas to dissolve into the liquid. And so we can go back to the idea of the soda here. This is why a sealed bottle of soda has a fairly high concentration of carbon dioxide. That little air space above the liquid has a high pressure of CO2. And when you open that top, what do we hear? We hear that pressure come out, trying to equalize with the atmosphere around it. And because the pressure of CO2 above that pop now is much less, then what you end up with is you end up with your pop eventually going flat as that CO2 undissolves from the liquid at the lower pressure. Here's some nice solubility curves of gases dissolved in liquids. So we have four different gases here. We have methane gas or natural gas. We have oxygen, we have carbon dioxide, and we have helium. And notice all of those curves decrease to some degree as the temperature increases. A couple of other kind of interesting graphs here are solubility of oxygen in water. So here we have freshwater versus seawater in the two different graphs. And we have the curves at three different pressures. And so we're looking at that blue line, which is at atmospheric pressure in both graphs. And you'll notice that more oxygen can dissolve in fresh water than can dissolve in salt water. And the other real concern here, right, is with things like global climate change is that when your average temperatures are higher, you actually get a decrease in solubility of oxygen in the water. And so there's less available oxygen in both fresh and seawater for sea life to be able to breathe. Let's look at just a quick example of how this Henry's law situation is used. So we have the solubility of methane, which is the major component of natural gas and water at 20 degrees Celsius. And 1 atmosphere of pressure is about 0.026 grams per liter. If the temperature remains constant, what will be the solubility of this gas at a pressure of 0.6 atmospheres? And of course, you would want to know this if you were, for instance, involved in fracking, which is a process of pumping high pressure water underground to dislodge pockets of oil and natural gas. And so you would be dealing with pressure differences there and solubility of that gas in the water that you're pumping in there. So here's our setup. S1 over P1 equals S2 over P2. And at 1 atmosphere of pressure, we have a solubility of 0.026. Notice we have a temperature in this problem, but nowhere in the equation does it really ask for a temperature. What you want to do is substitute your given pieces of information then into this equation. And so we have a concentration of 0.026 grams of methane per liter of, it could be a liter of water, could be a liter of solution, divided by the pressure, which is 1 atmosphere. That is equal to the new solubility at the lower pressure of 0.60 atmospheres. So if we think about the relationship of Henry's law, Do you expect that solubility to increase or decrease as you decrease the pressure? And hopefully, as you thought about that for a second, you would expect a decrease in the solubility. So if you're going to solve for F2, it means we need to multiply both sides by zero point 0.6 atmospheres. That's going to cancel the 0.6 atmospheres on the right. It's going to cancel the unit atmospheres on the left, which is helpful because you want your final answer to be in a solubility unit. And you end up with a solubility of 0.016 grams per liter. So there you have it. Those are solubility types of solutions and factors affecting solutions. And when we dive into the next video, we're going to get quantitative about how we're going to go about measuring these different solution concentrations.